Hi everybody. Let's get back to our solid state electronic devices. So problem. Um, this series going to be problem in chapter 3. So again, this is what I had when I was the student, a PhD student at Rochester University. Um, this is going to be your homework number 3. We have a total of 7 problems. And what I did, I rewrite solution. And we have probably about 8 pages. Okay, start from problem number 1. Let's see here. Let's blow this up a little bit. At room temperature, the band gap of a gallium arsenide is 1.43 electron volt. Assuming an infinite potential well approximation, what is the size in angstrom of aluminum arsenic, gallium arsenic, and aluminum arsenic quantum well, which can produce an effective band gap of 1.50 electron volt in gallium arsenide. Assume effective electron mass equal to 0.067 m0, where m0 is the free electron mass, and the whole effective mass m star h equal to 0.5 m0. So we still concerning about the quantum well. Okay, but this one we move to semiconductor devices. This is the diagram of electrons and holes in quantum well. I asked you about the size of potential well, which is the A in the picture. And we are gallium arsenide surrounded by or sandwiched by aluminum arsenic. And normally at room temperature, the band gap of arsenic is gallium arsenide is 1.43 electron volt. So this actually the band gap energy of gallium arsenide. But now when you have the potential well or quantum well, that will change your band gap, the normal one, to be an effective band gap of 1.50 electron volt, which is higher than the normal band gap of gallium arsenide, or 1.43 electron volt. So let's look for A, the width of our quantum well. Now I just pick up from section 3.2.5. You know that the band gap energy that's equal to h bar square k square over 2m, or p square over 2m, right, where p is the momentum. And your k, we have proved that equal to n pi over a, where a is the size of a quantum well. Now since we have both electron and holes, we modify the equation above for the quantum well. So Eg nu minus the Eg before, or the bulk, and Eg, this is from our quantum well. That's going to be but the difference is that you have both electron and holes, so that's why we have the term 1 over effective mass of electrons minus 1 over effective mass of hole. right? Because you not use the just M0 or the free electron mass. That's what the difference. So simply you rearrange the equation, the expression, and you have A equal to square root of these expressions. What you need to do, just plug in the number. You know that this is your h bar, that's the 1.05, 10 to the negative 34th, and then you square, pi square, and your delta E is just simply the band gap energy of a quantum veil, or the new one, and this is the old one, 1.43, that's become a delta E. And of course, you need to convert your unit from electron volt to joule, right? Simply by multiplying 1.6 10 to the negative 19th, that's the charge of electron. And your ME, effective mass of electrons, is equal to 0.067 M0. This is your M0. And MH equal to 0.5 M0. Sorry, MH star. And that's give you A equal to 95 angstrom. So your quantum veil, the width of your quantum veils also affect your energy band gap. So you learn from this problem. Okay, that's the problem. The first problem of the homework number 3. See, you have something else? Okay, no. Now, from the textbook, the problem 3.4. Show that the probability of state delta E above the Fermi level EF is filled equals the probability of state delta E below is empty. So basically you have, this is your energy band diagram. You have the conduction energy level and Fermi level and valence band energy level. And you have also intrinsic energy level, which is become in the middle between EC and EV. They want you to prove that the probability of the state delta E, which is higher than Fermi level right here, and also another energy level below EF. But this one looking for the probability that the state will be empty. That's going to be equal to the state, the energy state that above EF will be occupied or will be filled. So you simply pick up equation from the book. States that the probability that an available energy state at E will be occupied by an electron at absolute temperature T can be explained by this equation: 1 over 1 plus exponential E minus EF over kBT, where kB is the both mass, the constant. Now for energy delta E above EF, so you have your E become EF plus delta E, right? Because you have the energy level at this point. Let's give you this expression. Now for energy delta E below EF, that means your E become EF minus delta EF. That's the probability that the energy state will be occupied. But the probability that the energy state will be empty is the 1 minus this term, right? This is 1 for occupied. and you end up with the same of the probability that energy state is above EF will be occupied. So you compare it to these equations. That means they are the same. That's the problem at 3.4. Okay. Problem number 3. Okay, we move to the extrinsic semiconductor. Okay, not just actually not yet. We will move to later problems. But the problems number 3, if N0, this is the electron concentration for silicon at T equal to 300 K. They ask you where EF with respect to EI. Where's your EF? Repeat for P0 equal to 10 to the 16, where P0 is the whole concentration. Now from section 3.3.2, electron and hole concentration at equilibrium, divided by equation 325A and 325B. Now for silicon, your Ni equal to 1.5 10 to the 10th per cubic centimeter at room temperature, or 27 degrees Celsius, or 300 Kelvin, right? And you just plug in the number from this equation. You have EF minus EI. That means your Fermi level is above EI intrinsic energy level. You have N0 10 to the 17th, and Ni is the 1.5 10 to the 10th, and then you have EI above minus EF minus EI is the 0.407 electron volt, and this is the energy band diagram. Okay. Now for P0 equal to 10 to the 16th, you apply this equation. So that means for the p-type semiconductor, you will have EF below intrinsic energy level. This is the 0.347 electron volt, and this is your energy band diagram for p-type semiconductor. Problem 3.9 from the textbook. A semiconductor device requires N-type material. It is to be operated at 400 Kelvin. Wood silicon doped with 10 to the 15th atoms per cubic centimeter of arsenic will be useful in this application. Could germanium doped with 10 to the 15th per cubic centimeter antimony be used? AS is the antimony, right? I'm sorry, that's the arsenic. SB is antimony, sorry, my mistake. Well, this is your energy band diagram. For EF greater than EI, you know this is going to be N-type semiconductor, and EF less than EI, this one going to be a P-type semiconductor. You can go back to figure 317. At T equal to 400 sorry, Kelvin, your Ni is about 6.0 10 to 12 per cubic centimeter. That's the electron concentration. arsenic, which is donor or N-type semiconductor doping. Nd equal to 10 to the 15th, that's given. And from our equation of I have what from the previous Q plus N plus Na, right, equal to P plus N D. If you have no Na, so that means your Nd is about N0, because your N0 is what, 1.5 10 to the 10th, 10 to the 10th, right? So that's for 300 Kelvin. But for 400 Kelvin, you have Ni equal to about 610 to the 12th. So from this equation, EF minus EI, that's N-type doping. You have KBT, Ln, N0 over Ni. And N0 is about Nd, which is 10 to the 15th. And Ni at 400 Kelvin. That's from figure 3.17, that's the 6.0 10 to the 12. And that's give you EF minus EI equal to 0.17 electron volt. So this is still good to be used as the N-type doping. Okay, you still have EF above EI. But now, talking about germanium, doped with 10 to the 15th antimony, to see that still be able to give you N-type semiconductor or not. You take a look at germanium semiconductor at T equal to 400 Kelvin, Ni equal to 10 to the 15th. For antimony doping Sb, this is also 10 to the 15th. So you can see that N0 is about Ni, or your EF minus EI going to be 0. EF is going to be at EI, or intrinsic energy level. So this one is not good for application. You need more Sb doping or more Sb concentrations. That's the problem 3.9. Page number 12, 3.10. A silicon sample is doped with 10 to the 16th boron atoms per cubic centimeter. What is the electron concentration N0 at 300 Kelvin? B, a germanium sample is doped with 5 10 to 13th serbium atoms per cubic centimeter. Using the requirements for the spaceshot neutrality, calculate the electron concentration N0 at 300 Kelvin. For the spaceshot neutrality, this is the equation for the spaceshot neutrality. For silicon, let's take a look at part A. For silicon at 300 Kelvin, Ni is about 1.5 10 to the 10th per cubic centimeter. For boron atom, that's p-type doping or acceptor. That means Na is much greater than N, because your Na is given to be 10 to the 16th, right? So from a special neutrality or this equation, you end up with Na is about P0. And you also have equation P0 and 0 equal to Ni squared at equilibrium. That's from equation 24. Since you already know P0, you'll be able to calculate for N0. That's end up with 2.25 10 to the 4th per cubic centimeter, or that's your electron concentration. Okay. B for SB, this is going to be a bit long calculation, and you have to think about this a little bit. From the surface charge neutrality equation, okay, since the concentration doping of SB, that's the 5 10 to the 13, when you compare to 1.5 10 to the 10th, you cannot neglect this number. So it's not much different when compared to A, which is the concentration is the 10 to the 16th, right? So you have to be careful about the calculation. All right, hold on a second. Okay, sorry, let's continue. So to find N0, you need to apply both equation at 327 and 324, which is these equations. So your PO equal to Ni squared over N0. Again, this is simply about the math. Your N0 going to be this expression, where your Nd is the 5 10 to the 13th, and your Ni is 1.5 10 to the 10th, and that's give your N0 become 6.04 10 to the 13th per cubic centimeter. Problem 3.15. A silicon sample is doped with 10 to the 16th boron atoms and a certain number of shallow donors. The Fermi level is the 0.36 electron volt above EI at 300 Kelvin. That's the N-type material, right? Because your EF is above EI. What is the donor concentration in D? B, a silicon sample contains the 10 to the 16th indium acceptor atoms and a certain number of shallow donors. The indium acceptor level is the 0.16 above EV, and EF is the 0.27 EV above EV at 300 Kelvin. How many indium atoms per cubic centimeter are ionized or neutral? So this problem become interesting problem for B. Okay, you need to think a little bit. Let's work on part A. What they ask you for? What is the donor concentration in D? Wherever silicon is doped with both Na, boron, and Nd, and at 300 Kelvin, Ni equal to this 1.5 10 to the 10th per cubic centimeter. So from this equation, that's the boron acceptor, right? P or 0 become 1.38 10 to the 4th by applying this equation. And simply you be able to find N0 by this relation Ni squared equal to N0 P0. So this is your N0 or your Nd. You can approximate this to be Nd because the Nd is the higher, much higher than Ni, which is one in the order of 10 to the 10th, but this one is 10 to the order. This is in the order 10 to 16, right? Now for B, okay, sorry, not finished yet. And this is for your Nd. And for Nd, you need to apply this equation N0 plus Na equal to P0 plus Nd. That's the the chart neutrality, right? And this is your band diagram, energy band diagram. Part B. This is the energy band diagram given. You have our EA above EV 0.16 electron volt, and EF is above our EV for 0.26 electron volt. As you how many indium atoms unionized ought to be still be neutral. Well, you see that the probability that EA states are filled follow this equation. If EA equal to 1 over 1 plus the exponential EA minus EF over KBT, where your EA is there and EF, that's the different rate, divided by KBT at 300 Kelvin, which is the 0.0259 electron volt. Your FEA is 0.979, not equal to 1. So that means some indium atoms are unionized because this is not equal to 1. Then the number unionized indium atoms is going to be 1 minus, this is the probability, and multiplied by the starting indium concentration, which is the 10 to the 16th rate. And you have the number of unionized indium atoms become 2 by 1, 10 to 14th per cubic centimeter. Last problem for the homework number 3. Using the requirement for the space chart neutrality, calculate how large Nd over Ni must be, where Nd is the donor concentration, in order for minority carrier concentration to be less than the fraction F of the majority density. Sorry. Well, you have to take a look. What you're looking for is the ratio of minority concentration, which is the N by the majority. Concentration rate or majority density. This is the Nd, and Okay, they ask you for ND over NI. So your NI become majority density, and this is minority carrier concentration. So that's what you're looking for, ND over NI. How do you start? Well, from spatial neutrality, you have these relations, and also this one, NP equal to NI squared. From 1 and 2, you'll be able to look for, this is the, what? Majority concentration, right? Because N is the N-type. And this is the minority concentration. And your F divided by minority carrier concentration over majority carrier concentration. That means you're looking for Pn over Nn. And you already, from equation 1 and 2, you already solved for Nn and Pn. You notice NA drop out because the ND much greater than NA, or you simply have only ND, the donor concentration. Then your F simply become the ratio of Pn and Nn. Okay, and this is just about math. You can follow, the ratio you're looking for, the ratio of ND over NI. So I put this one, I take the common term out. That's the ND squared. And ND and D cancel out. So you end up with this. And I let X equal to NI over ND. And you solve for ND over NI, which is equal to 1 over X, right? Because you start dividing X as the NI over ND, so your ND over NI is simply equal to 1 over X. And that's equal to 1 minus F over square root of F. That's the fraction. For F equal to 1 over 10, you can find the ratio of ND over NI, as well as the F equal to 1 over 100. So that's the ratio of the minority carrier concentration and majority carrier concentration. Okay, that's all for solve problem of the homework number 3. And we will talk about more on the electrical properties of materials in next series. Okay, bye.